I'm Simon Frikopoulos. Thank you for having me here. I will more or less continue the previous talk. I will dig into how we develop geography for boost geometry. So you can think of it like a more low-level introduction of how geometric and geographic algorithms are working. So this is more or less the outline. In the beginning, I will give maybe very basic definitions of the objects, and then I will give some examples of how can you compute stuff in boost geometry. So the most simple model that you can have for Earth is the flat Earth. That the problem is that there are some people that believe that this is the only model. Okay, we'll go for something more rational. We'll think that the Earth is has more models. So having flat model, we have accuracy only locally. It's easy because you can use Euclidean geometry. It's very fast and simple algorithms. But if you want to go a bit more accurate, so we can assume that the Earth is a sphere. This is widely used, for example, in Google Maps. It's not very accurate, but it's better than flat. And we have fast algorithms. I will explain a bit what I mean fast algorithms here. And then we have an even better model, which is the Earth as an ellipsoid of revolution. This means that it's a bit flattened in the poles. And this is the state of the art is in GIS, as far as I know. And now you have more involved algorithms to implement. And of course, if you want to go even further, you could have a geoid, where you have also the center of the mass of the Earth. And this is for special application in geophysics. So we go up to here in boost geometry. We don't do the geoids. So this is some types. This is coordinate systems in boost geometry. So we have a Cartesian type, and we have a spherical equatorial parameterized by either degree or radian, and we also have the geographic. So geographic is the spheroid in the previous slide, and this is the sphere, and this is flat. Okay, so the basic objects in our study are geodesics, which are the shortest paths between 2 points. So in the flat, this is a geodesic is just a straight line. In the sphere, it's a great circle. So you take the sphere and you intersect it by a plane that passes through the center. You have a great circle. And in ellipsoid, the geodesic is not a closed curve. So this is somehow, this gives you the complexity, increase a bit the complexity. So this is how it looks like in the ellipsoid. So this is a geodesic. It's not closed, so it iterates through the globe. And it does not have a closed formula. Okay, except meridians and equator. So meridians and equator, we have closed circles. I mean, it's actually like great ellipses. Okay. So, okay, this is just a note that there is also this loxodrome or ramp line that you can see in maps of if you use the Mercator projection. So if you draw a line there in such a map, then this is a curve of same angle that crosses the meridians in same angle or azimuth. And the great circle there, the shortest path is not, of course, that ramp line, but goes around. So this is just not to confuse loxodromes with geodesics. So loxodromes are easier to compute. So we want to compute the geodesics, the shortest paths. Okay, so these are two main problems in geodesy, and these will be used as core procedures to build more complicated algorithms. So we have the direct problem when we're given a point, the azimuth, which is the angle, and a distance, and we want to compute the point, which is that distance away, and it's the given angle. So it's like navigation. And then we have the inverse problem where we are given 2 points and we want to compute the distance and also the angles. So having this, assume that somebody gives us this implemented, then we can start building some core geodesic algorithms like point-to-point distance, area of a polygon or other objects, intersection, envelope, all these kind of algorithms. And then using this, we can have higher level algorithms of like geometry distance, like a distance of a multi-polygon with another crazy multi-polygon. And then we can have a set of set operations in geometry like union, intersection, etc., and relational operations. And this can be used if we want to build a spatial index. So the main problem here, as you can realize, is the distance of 2 points. So all of these algorithms need to compute the distance between 2 points. So in flat, you have you knew everything from primary school. It's a Pythagorean theorem. It's quite simple and also simple to implement it. Then for sphere, okay, again maybe high level, not primary school but high school. You have again we have a closed formula. It's easy to implement. Uses some trigonometric functions, and then when we are in the ellipsoid, there is no closed formula. So this is the equations that connect the distance, which is s here, with the longitude, latitude, which are lambda and phi. So I will not, of course, explain these formulas. Just have it here for illustration of how the difficulty goes, and you can also 2 points here, 2 comments. You can realize that going down, we increase accuracy. Also, we increase complexity, which means that our code, our implementation will be slower. Okay, so what we do in Boost Geometry, we have different formulas which are selected internally with respect to the coordinate system. So as Adam shows, the coordinate system comes together with a point. So if you define a point that is geographic and then start applying algorithms on this point or geometries that you construct with this point, then internally the Boost Geometry will call either the more complicated algorithm for spheroid, or if you have your point, if your point wants to be on the sphere, it will run the more easier, faster but less accurate algorithms for the sphere, for example. And also, this is in more detail. We have for ellipsoid, we have 3 different algorithms that are these 3. Okay, we call them strategies, and there are 3 different ways of approximating the distance, and there are some some time accuracy trade-offs. So the first is less accurate but faster, and so on and so forth. And we follow the state-of-the-art approach, which is that in all these geodesic problems, actually you solve a spherical problem, which is easier and has a nice closed formula. And then you do some ellipsoidal correction by solving some integrals that similar to the ones I showed before, either by series expansion or numerical integration. We do series expansion, which is enough to have good accuracy. If you want more details, we can discuss it offline. So I think this is enough for the details of the implementation. So again, I will give a similar example as my colleagues. I'm from Athens, so I calculate the distance from my home to the event. I use Boost Geometry for this. Probably you have understand from Adam's talk what all these definitions are about. Here I also define a spheroid, and I define a strategy, which is, let's say, Thomas. It's one of these 3 strategies that I showed before. And then I asked to compute the distance from the point, which is Athens, let's say Acropolis, which is more fancy, and the other point, which is ULB Brussels here. So, and I say that I want to use this strategy. And then I do the computation. If I remove the strategy from here, the default strategy will called. And also if I go here and put, instead of geographic into the points, if I say that these points are spherical, then the same code will compute the spherical distance. Okay, so I run some examples with boost geometry, and these are the results. So with spherical, I have this distance. Spherical here, I use a different radius. So these are both spherical, but with different radius. And as you can see, it's the same as Google Maps. So Google Maps give me this distance, which is the same as this one. So this means that we understand that Google Maps uses the formula that I showed you before for spherical, and also assumes that the radius of the Earth is this one, which is the mean Earth radius. You can also use the WGS 84 major axis of the ellipsoid, make a bit larger radius, and you have a more accurate result. But I guess this happens only in this example. So this does not mean that if you use this radius, you have more accurate results. The only way to have more accurate results, if you want, is to use the geographic. So these are the three different strategies that we have implemented: Andoyer, Thomas, and Vincenti. And as you can see, the divergence is quite small between them. And the result is has something like 2 or 3 kilometers difference from spheroidal, which is Google Earth. Okay, so a normal question here is, again, what's the performance?
What is actually the distance?
The actual distance is, no, should be this. The actual distance, yes, how do you compute the actual distance? No one knows. A survey engineer should start from Athens and start shooting. Yes. So, okay, another example. So this is Brussels Center. It looks like a pentagon. So I just created a pentagon. And I asked for Google Maps to compute the area. So Google Maps compute that area. I will show it the second slide. Yes, before showing the area of Google Maps, I use Google Maps to compute the area, and then I put the points inside the boost geometry to compute the same area with boost geometry. As you can see, this is similar to the previous example. I have again a strategy for area, which is geographic and is parameterized by the Vincenti formula. You can parameterize it with Andoyer or the other, the Thomas. And then you create one strategy and you plug it in to the computation of the area. If you leave it as it is, so if you remove it this and you say area poly, it will use the default, the one that we believe is better, but you can use your own. Okay, and these are the results here. Again, Google Maps looks at, again, it's using this mean Earth radius and gives this result. And these are the results with geographic algorithms. Here, even in this smaller example, you can see that, again, there is a difference in accuracy. Okay, so performance, what is expected is that the spherical is less accurate, and then Andoyer is a bit more accurate, Thomas is a bit more accurate, the most accurate one is Vincenti. This we know from the theory how these algorithms are working.
We don't know the actual distance. How do you know this is the most accurate?
How you know? Okay, because you know how these algorithms operate. So actually these algorithms create some series, and this algorithm, let's say, very high level, cuts the series in some small order. This goes to a higher order, and this is using a better algorithm with Newton iteration. Okay. So, in theory, this computes a better and more accurate result. So, okay, we don't have a detailed performance analysis, and it seems that we also don't have accuracy analysis that a lot of people seems that they question. But yes, I don't know if you have feedback or where if there is a database of I don't know, accurate distances, we could try to see the accuracy to make a study. But also it's interesting to do a performance analysis of these implementations. And yes, we have some timings in GitHub pull request. So while we do the pull request of these features, we also write some tests for in our computers. But okay, of course, this is not a detailed performance analysis. Okay, so similar work. There is this library which is called Geographic Lib. It's again C++ and also implements similar algorithms. It's robust and it's fast as far as I know, and it's also used in PostGIS from this version and on. The thing is that it lacks a variety of algorithms, so it only gives you the distance, area, and some special projections. So we are even now have implemented more in boost geometry. And yes, just a tip of performance, just testing in my computer Geographic Lib for distance and our algorithms for distance. Our implementation is faster, but of course this is not a performance analysis, but it seems that I don't know, at some point we have a faster implementation. Okay, that's it about the related work. And let's go to future work. We are ongoing. This is work in progress. We are implementing more algorithms for ellipsoid, like segment distance, more projections, convex hulls, and droids, and actually we also want to have all the relational operations that are going to be used for spatial indexing. And yes, this is an open problem. I mean, this is an open feature. We don't support distance of near adipodal points in geographic algorithms. So this is something that at some point we want to implement in boost geometry. And also we are thinking, that's why we have this face there, of Google Summer of Code proposals. But we don't think, we are not sure if we propose something, but we are thinking of some projects. So yes, keep in touch if you are interested. And yes, that's all, I think.
Is it possible to implement my own coordinate system? So, for example, I have specific arithmetic for coordinate system, and I want to use a library, but I cannot do it because I have specific coordinate system. Can I implement something and put it into?
Can you repeat the question?
Yes. The question is if one can implement its own coordinate system. But what does it mean, its own coordinate system? I mean, something. I mean, how do you define?
Some that there is a digital integer number arithmetic with overflow, with exploiting overflow for calculation distance and on coordinate, and it's quite specific, and it differs from any Cartesian or spheric or spheroid system. It differs.
Okay, so it's a special coordinate system. So I guess if you want to do this, you have to at least implement how the distance between 2 points is computed, at least this, and then you can probably use all the other algorithms that use the distance as a main procedure. But then, for example, for area, you have to, area cannot directly call distance. It's a different algorithm. So for area, for example, it depends on what you want to use. For example, if you want perimeter, you can implement distance, and then you will have perimeter for free. But for area, for example, you have to implement again an algorithm that computes the area of a polygon. But I guess this is.
It's possible, but it's a lot of work.
You have to. Yes, you have to implement at least. How do you measure the distance between two in this coordinate system?
It's still useful for some things you get for free.
Yes. Yes.
It will all work automatically.
Okay.
Yes.
Do you have any thoughts on implementing the set theoretic operations like polygon?
Union and yes, I think I had it. Yes. There is a.
What are you using
They are already there in technical environment, but they need to be implemented in the
So the operations are there. You can perform union of polygons, for example, if the polygons are Cartesian. So the algorithms will remain the same, but somehow we have to do the work of plugging in the geographic system, for example. If you want to do unions of geographic polygons.
And the current algorithms, I suppose, what?
No, it's not open source because this is based on graph proposal and nothing is based on Swift. Whose polygon is based on that? The overlay of two polygons is completely different.
Is it possible at all to read it from the algorithm
Okay. Well, yeah, just go one more question. It's good.
Just one. We have also the comparable distance, which is supposed to be much faster.
Yes.
For Cartesian and for spherical.
Yes.
Do you think it's also
Makes sense.
even possible to implement such a thing in geographic?
So this has to do with square roots. You don't compute the square roots, and yes. I haven't think of it, but it's not straightforward because you don't have a square root. You have some iterative method that approximates some integral, actually. So I don't know how can you gain from this, but maybe you can do something, not end the computation at some point when you know that the one result is larger than the other. Maybe you can stop it. I don't know, something like this. Yes, this could be useful.
Okay, thank you.
Thank you.
We have to finish.